Hello. Well, the title of this presentation says literature review, although it won't really be a literature review. The basic problem is that in this research, we have a number of algorithms that we've implemented to solve the same problem. They vary a lot in their methodology to solve the problem, and of course, they are standard approaches in the literature. Now we cannot end up filling the entire matrix how every approach is different from every other approach in the literature, and how the different approaches are different with respect to each other, which one is better, which one is not better. So instead here in this presentation, what I'll be doing is that I'll very vaguely explain some of the very basic concepts, some of the very basic terms used in the literature review provided in the thesis. Interested readers who are not very familiar with any of these domains may just take it as a teaser of all the various possibilities that exist, the rich literature that we have. It's even possible that you entirely leave this video without affecting any of the readability for the subsequent chapters or for the subsequent presentations that I have. The thesis basically has two independent parts. One is the domain of trajectory planning of autonomous vehicle. The other is how do we manage the transportation system at large. We'll be dealing with both of these one by one. And for trajectory planning of an autonomous vehicle, I may take up the algorithms from the domain of intelligent vehicles or from the domain of mobile robotics. We'll seeing one by one what are the trade-offs in each one of them. Now, when we come to the problem of trajectory planning of an autonomous vehicle, and we try to use the existing algorithms in the domain of autonomous vehicles or intelligent vehicle, the basic problem is that these algorithms are made for a lane oriented traffic where the traffic is completely organized in lanes. So we've got the vehicles cleanly following the lanes, and one may either change lane or travel straight, or change lane, travel straight, and then again return to the lane, which is the overtaking phenomena. There are algorithms which deal with obstacle avoidance, even though they may not be assuming the lane, but what they basically do is there's a simple obstacle framework and they try to make in simple methods to overcome this obstacle. What we'll be dealing with a very complex obstacle framework, and how do the different algorithms cope up with that, how do they behave to that. The notion of cooperation is completely different, what we call and what the standard literature call. Standard literature is of course for lane oriented traffic. So all it means by cooperation is when a vehicle should change lane in order to cooperate with the other vehicles, and when it should not change lane. Whereas by the term cooperation, what we mean, suppose there is a vehicle ahead which is a slow moving vehicle, and hence a fast moving vehicle would need to overtake it, and suppose this is the fast moving vehicle behind. If this vehicle does not move, the vehicle behind in order to overtake will have to take this complete trajectory, which is very long. Instead, if it moves a little on the side, depending upon how much distance is available, if it moves a little on the side, then it may take in a little easier trajectory. And that is what we will call as cooperation. This side movement, which is apparently very common in the unorganized traffic that we are dealing with, a vehicle is supposed to move on the side to allow an easier overtake of the vehicle behind. That is what we will denote by the term cooperation, and not anything what the standard intelligent vehicles literature says. Mobile robotics is of course much more interesting domain. It has got nothing like an organized structure, an organized way in which the robots travel. Of course, there are algorithms which assume rectilinear moves, but those are very few and not very commonly used in modern day times. So when it comes to the domain of mobile robotics, I have some kind of map. I have got multiple robots who move around in this map, and the objective is to make these robots move to some goal, which is much like what we are saying, except for that our notion is of a road, some vehicle here, and the two problems of course sound very similar. In both they are obstacles and a robot moving from one position to the other. However, largely when we study the literature, when we see the literature, the mobile robotics algorithms, they either assume wide open spaces where there's no narrow corridor like this, or they do not necessarily assume, but the algorithm performance drops miserably. In fact, this is a standard problem denoted as the problem of narrow corridor in mobile robotics, where the algorithms either fail when the optimal path passes through a narrow corridor, or they take very long time. And we basically understand that generating a random sample inside this narrow corridor, I taken a random number and I say that what's the probability that it lies inside this, it will be very low. So sampling based approaches which rely on random samples will fail, and similarly the other approaches will fail. So the problem is, how do we work on a scenario which only has narrow corridors? That will be one challenge. And what we'll be doing is, in place of taking it as a limitation, we'll exploit the underlying road architecture, we'll be exploiting the underlying narrow corridor architecture to benefit and generate results even faster using the existing mobile robotics algorithms. The other is a much more important point. Now, in entire mobile robotics, we never come across scenarios where there's one robot which is following another robot. The two will usually have very distinct goal. This will go like this will go like this. And hence we either only optimize the path, or we optimize the path and the speed, but in both robots we consider any possible speed. While in roads, what happens, suppose there's a vehicle here and there's a vehicle here, we all know from our natural driving, from our natural instincts, from whatever we observe in practical traffic, in an unorganized traffic, it'll basically either follow or it'll overtake. If it follows, then it'll continue to follow till condition becomes feasible for an overtake to be possible, only in case this was at a higher driving speed, this was capable of higher driving speeds. So it makes a lot of sense to make the speed of this robot nearly equal to the speed of this robot, which does not make any sense in robotics. So basically we see this wonderful concepts of overtaking and vehicle following, these wonderful concepts are completely absent in mobile robotics, and therefore we need to optimize against a much varied space. Basically there are infinite possibilities. We need to compute all of them in mobile robotics. So an amazing thing which will happen in this research is, we'll use the algorithms which are known to be very time costly, which are known to be very expensive in mobile robotics, and they'll run perfectly in intelligent vehicles, in autonomous vehicles, because we'll be using these as heuristics, and we'll be using these two phenomena as heuristics to bias the general algorithm framework of mobile robotics. So that's something amazing that will happen. In fact, what's more amazing is, we know all the algorithms perform terribly in these narrow corridor kind of situation. Because of these heuristics, they'll start performing very well, which is what basically the thesis was all about. Now, when it comes to the intelligent management of the transportation system at large, these are the three sub-problems that we would be dealing with. And there's a fundamental difference between what we do and what the literature does. Now, we take in this concept very seriously. That is diversity. And in fact, this is what made the unorganized travel much better than the organized counterpart, that was diversity. Now, the approaches that we present will not, for the intelligent management of the transportation system, they won't be valid for an unorganized traffic. We couldn't do that much amount of work. They are valid only for an organized travel, but nevertheless, we cannot take in size-based diversity. We will take in speed-based diversity, where the vehicles will have very different speeds, or what we call as task-based diversity, where the different vehicles will behave very differently depending upon what they are up to, depending upon the task for which they are traveling. So we are basically kind of exploiting something that we know from the application domain or from the final domain in which these application would be implemented, and we're kind of implementing some diversity over there. That is how we differ from literature, whereas literature just says these are vehicles almost similar and these just need to go from their source to their destinations. From here, I'll only be taking in broadly what the different approaches are. I'll select a few of these per slide. There are approaches which are clearly for structured environments. Structured environments mean that I know that my obstacles are pentagon, polygons in general. I know their sides, I know their centers, I know the coordinates of these, and therefore what these kinds of approaches do, like the one mentioned out here, they would form all types of triangles. These are polygons, so I can easily form triangles out there, and then select based on the sides, selecting in the optimal trajectory. Here, of course, in the work that we do not assume a structured environment. They can be any shaped, arbitrary shaped obstacles. We know them as an image file, we know them as an obstacle function, but we do not know what geometry they have. The geometry is completely unknown. Similarly, what intelligent vehicles mostly do, I've dealt with cooperative overtaking where they allow or disallow a lane change depending upon some optimization. What they more do is they are assistance system which see that the vehicle is in front, it sees the distance from the vehicle in front, behind, and all around, and it tries to assess whether it is safe to make a turn or the vehicle should be disallowed to make a turn. There are some which do that. There are some which see it is safe to make a turn and automatically make an overtaking trajectory or automatically make the vehicle overtake, or if the human is overtaking, disallow the overtake depending upon their whether the algorithms are for driver assistance system or for autonomous driving. So that's all the things that they do. These are algorithms from the domain of mobile robotics. Now, one of the very widespread algorithms used are all the optimization based approaches. The genetic algorithm in particular, very widely used in mobile robotics. The general variants where we optimize a set of points are very common. Sometimes what we do in this is every optimization based approach basically needs to find out whether this path is obstacle free or it is obstacle prone. So one of the trick that we use is, instead of checking each every iteration, every generation, each and every point, I check some random set of points at some intervals, and this interval keeps reducing. So initially I have only a vague idea whether a path is obstacle prone or obstacle free, which enables me to compute a very rough or very vague trajectory. And towards the later stages of the algorithms, I check in all the points, and hence the complete optimized trajectory is known. So that's multi-resolution planning, or planning from higher resolution at start to lower resolution at end. And what is these days very common, especially for multiple specific task robots, we know these are the common situation which a robot faces. For this situation, this is the optimal trajectory. For this situation, this is the optimal trajectory. We make in a database, and whenever a new situation occurs, we find the closest situation in our database. We see how do these two situations differ, what is the difference, and we try to interpolate that. If this was the optimal trajectory for this scenario, what will be the optimal trajectory for this new scenario that we have seen. So these are like pre-computation or database approaches. The problem we are solving is for multiple vehicles or multiple robots, so the approaches may be centralized, where every combination of every robotic move as a single optimization problem is solved. And of course, as the number of vehicles grows or the number of robots goes, it grows massively, and it's practically never used. Decentralized plan, each and every one separate, Of course, the centralized would mandatory assume some kind of communication between the vehicles or the robots, and decentralized would also assume some kind of communication between the robots unless you've got some good coordination technique which can work without communication. The cooperative coevolution is intermediate. As in decentralized, there are multiple agents. Each agent is responsible for different vehicles. So this agent responsible for vehicle 1, this agent for vehicle 2. So as in decentralized, they all evolve, they all compute their trajectories independently, except for two things. One is, in cooperative evolution, even if this solution is bad, if it enables some other solution to be good, it is given a good fitness, or it's given a good cost. And secondly, there is a centralized agent that coordinates between them or finds the best combination of these solutions. So that's cooperative coevolution. RRT these days seems to be like a real hype word. A lot of work, especially the recent literature, makes a lot of use of these methods, which is rapidly exploring random trees. The actual RRT I'll be taking up later in one of the approaches, where I'll be basically briefly denoting what an RRT is. But RRTs are suboptimal. So one of the ways to make them optimal is run them 20 times, which will generate 20 different parts per instance, and then I say I formulate my final part. This much came from the 16th RRT where this part was the best. This part came from the 18th RRT where it was the best. This part came from the 5th RRT where it was the best. So I basically generate 20 different solutions and create a method to solve them up. There's a lot of work in where RRT generation should be explored, because what RRT is, there's an obstacle framework, there's a source, and there's a goal. It'll try to cover the entire map in the form of trees, so it'll try to generate solutions like this. If I can bias these solutions, if I can bias these samples, so there's a lot of work in designing good heuristics. Of course, we do not, what we would be presenting here, will not be using heuristics for RRT generation, but we'll be using the heuristics of vehicle following, vehicle avoidance, and the general traffic as we see into the RRT generation. So that's completely different. And as I mentioned, narrow corridor is a very big problem in mobile robotics. So if this was the source, this was the source, this was the goal, the RRT generation will have very difficulty in entering this corridor. So retraction based RRT says if a sample is generated here, my basic problem was the probability of sample generation here was very low. So retraction based RRT says if a sample is generated inside an obstacle, migrate it to the nearest obstacle free region. And hence we see that any sample generated here or any sample generated here would ultimately be promoted to this place, and the probability will increase, and it will become very easy to migrate this narrow corridor, which is a major problem in mobile robotics. Multi-resolution planning comes very natural from how humans plan. If I give you a general maze-like problem to solve, there are some obstacles out here. What the graph search methods do, they generate a complete graph out of it, and the planning complexity and correspondingly the optimality and the completeness is depending upon what is the resolution of this map. So if it's an m cross n resolution file, if m and n are very high, the solution will be very good, but same, it will take very long time. So what multi-layer planning says, initially form solutions at very low resolution maps, and then as the algorithm proceeds, find solutions at higher resolution maps. So we basically start with low resolution, and then as the algorithm proceeds, we have high resolutions. Of course, there are various variants of it. Some iteratively plan the entire path, whereas the other use low resolution map some use low resolution map for the actual planning and the high resolution map for the cost computation. The low to high resolution, if I restrict it to exactly two levels, that is, there is one low resolution level and the one is high resolution level, then it becomes a bi-level planning, which is a two-level planning. So basically the same map, I have got a low resolution version of it and a high resolution version of it. So a simple thing that I can do is use a deliberative planner use a complete planner, use an optimal planner for this thing. Because the resolution is low, the path will come, approximate path will come very quickly. That will be good. And then using this path, I use a reactive planner or a suboptimal planner or a very fast planner which is biased towards this path. So basically, I get the advantages of deliberative techniques and the reactive techniques using two layer planning. And what the adaptive roadmaps are, especially a result of the advances in multi robotics. If I've got a robot here, if I've got a robot here, if I've got a robot here, these three can communicate to each other. There are some obstacles out here. This one will build a small roadmap around this region. This one will make a roadmap around this region. This one will make a roadmap around this region. There might be another robot around this region, and they'll share the information. So every robot knows only little, but together they know a lot which can be shared. So those are the distributive roadmap based approaches, and these are the reactive methods which are very fast in planning. They see the immediate scenario and take a very rapid decision over it. The distance maximization based approaches basically say that every unit move should be such that the distance from the obstacle is the highest. So if this is the scenario, it'll see that how can I get the maximum distance. Either I go here, the distance will increase from this obstacle, or if the goal is here, I might basically take in midway or between these two. Logic set is like how we plan. There's always a logic, there's a set of there's a logic base, there's a rule base which covers how we move. If it's discrete, it's logic set. If it's a fuzzy logic base or fuzzy rule base, it's fuzzy base planning. The velocity obstacles are if I have got only for structured obstacles or only for obstacles where the geometry of the obstacles are known. If I've got two robots here, one is moving like this, the other is moving like this, the speeds are known. If we see the relative motion with respect to two things, they are this robot can do two things: either go like this before this robot or go like this after this robot. And this robot hence acts as an obstacle, as a velocity obstacle for this robot. We take both into the consideration. We say that these speeds are not, we find out the speeds which are not allowed. The converse is the speed allowed for this combination of robot. If there's another robot V3, we find out the allowed and this allowed speed for this with respect to this robot. The minimum speed is taken for the navigation, which are the velocity obstacles. So this was more or less all the major algorithms that have been mentioned in the thesis. It's a very big domain in itself. For routing, there is again a lot of work for the specific problem of routing, which means finding out a route or the set of roads to be followed in a road network map of the city. So if this is the city, in finding out whether the vehicle should move like this or through this way or whatever. The anticipatory systems, they assess the current traffic scenario, they predict what will happen in the future, where congestion will be large, where congestion will be small, and hence they try to make the vehicles move by the possibly lowest congested areas of the future. Reservation is when I can book a lane, when I can book an intersection, when I can book a part of a road, etc. based on some monetary value or based on some other heuristics or other reservation policy. Digital pheromone is if I have got this simple road structure, every vehicle that passes through this route, it deposits some digital pheromone out here. So the next vehicle which enters knows basically how much amount of pheromone is there, which is an indicator of how many vehicles are there here, which is an indicator of what is the traffic congestion, and automatically it may try, if the congestion is too much, if the pheromone is too much, it will try to avoid, and the pheromone will evaporate with time. That means if no vehicles come here into the future, the next vehicle which comes, it'll see that all the pheromone has evaporated, so it'll again be very likely that it takes this route. That's the pheromone based planning. And then hierarchical planning is something very common discussed in AI. If I want to go from Reading to say Edinburgh, then I do not consider the roads around my house. What I consider is there is Reading, there is city A, there's city B, there's city C. I consider this kind of map. I find out the cities to be connected. Then in Reading, I see that I decide which motorway is to be taken. How will I go to the motorway? From this motorway, how will I enter city? How will I leave city? Now, this is of course, at the level of a country. People have done it at the level of a city or a metropolitan, where they have identified that this is one area, a very posh area, a very nice area, a very well connected area. This is another area. This is another area. So these become the communities, and a hierarchy planning is applied from one community to the other community. And the last thing that I would be taking is the problem of start time prediction in the thesis. Now, what literature says is that whenever I want to travel from road A to road intersection A to intersection B using some existing road. Now, what we do not discuss at the preliminary courses or in preliminary research is that the time that it takes to go from A to B is actually stochastic in nature. There is a probability distribution of time with respect to the probability. There's no discrete time. We cannot say that it will take 2 minutes, it will take 3 minutes, it will take 4 minutes. There is a distribution over it. So if I model all the roads like this, if I model all the travel times like this, if I model the probability distribution at every set of nodes, I'll get in a Markovian process which I can based on which I can optimize the route or the time. And basically they are stochastic graph search, which consider every combination of probability distribution for every combination of roads, and hence it's a very time complex exercise to find out a route from start to the destination. And of course it cannot be done on very large graphs. And similarly, there are travel time prediction problems. What they try to do is that they try to predict how much time will it take from road A to road B based on historical data or based on live data, whatever may this be, whatever the case may be. They try to predict how much time it will take from A to B, and based on this time prediction, I can basically use my graph search over the road network graph in order to predict the best route and the best time to make a journey. And the subsequent chapters, of course, will not make any reference to this. This was only a broad overview to assist in thesis reading or a general overview of robotics. Thank you.